Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Let us get into it, right into it. So we are still doing a lot of exploration in the land of series. So I just want to continue on that. So sets, I meant. So we have spoken about sets. These were unordered collection of objects where repetitions are ignored. We saw the notation for how we can write them down. We know what it is for two sets to be equal, determined by their members. Every now and then we want to care about things like order and repetition. And so we can invent this new thing called tuples. And we'll see where the difference between these two come up in later sections. So we have n tuples, n sets. We looked at what finite sets mean and infinite sets mean. It kind of just means intuitive what you think. Finite sets just means, you can count it and eventually you can count everybody and you can stop. Whereas infinite sets, you can't do that. There's something called the empty set, which is a very important idea, the idea of an empty collection. We also saw what subsets were. This was like if I have a set and I want to create a sub-collection of that set. So someone made a collection and then I'm taking from that collection to make a new collection. This new collection is called a subset. And we saw that that's the symbol for it and what it means. The empty set is a subset of every set. Every set is a subset of itself. And two sets being equal means they're subsets of each other at the same time. And we did some examples of that. We also looked at power sets. This was the set of all possible subsets of any given set. We saw that if a set has n elements in it, so it's a finite set, the power set will have 2 raised to the n elements in it. And we kind of did a very small illustration of why that is. It's because you have to make 2 choices for every element in the set. And then there's something called the multiplication rule, which we will talk about in a later section that would tell you, oh, well, that's how many total possible sets you could create, is you would just multiply all the choices that you have, right? That's called the multiplication rule. And we sort of stopped right there. We still have a few concepts to talk about when it comes to sets. And we still want to be able to do things like operate with sets, like do mathematics, quote unquote, with sets, as well as visualize set operations. So that's what we're going to talk about today. So let's actually just, someone's trying to get in here. So let's just continue. So we're still, effectively in 7.2. Okay, what is the next thing I wanted to tell you about? There's something called numerically equivalent. So let me mention that definition. 2 sets, A and B, are said to be numerically equivalent. Now, the numerically is sometimes left off, especially in text, but usually when people are saying it in words, they would actually say the word numerically. And that's because equivalent and equal, sometimes people think of them as the same thing, but they're not. And so it's very easy to mix up equivalence with equality, and they're not the same thing. So sometimes people will emphasize, I'm talking about numerical equivalence, meaning they're equal in terms of the number of elements they have. So numerically equivalent if the number of elements in A is equal to the number of elements in B. So example, let's say my set here is 1, 2, 3, and I have my B set here is A, B, C. Then clearly, A is not equal to B. They're not the same. They're not equal. However, but the number of elements in A and the number of elements in B is both 3, which means they are numerically equivalent. So in terms of the number of things they have the same number of things. And sometimes it's important to know that they have the same number of things more so than what the particular things are. And we'll see a few cases where that would come up in probability, not a lot though, but in mathematics, it's actually a big thing. In mathematics, it turns out that there can be things that look very different and that would seem very different to the eye, but you can actually prove mathematically, they're essentially the same thing. It's like you can take this set over here, everyone goes into witness protection and they're relocated over here, so all the names are different and they're in a different environment, but it's like they're all the same people. They behave exactly the same way. And one of the ways you would figure that out is first by figuring out how many of these things are there, right? Like you realize, well, in this city over here, there were 10 people. And suddenly over here in this city, there are also 10 people. It's very strange that there would be exactly 10 people over here when I know about these 10 people over here, and they kind of behave the same way, right? So sometimes you have to think about how many things there are more so than the actual thing. So we invented this definition to actually keep track of that. So it turns out that I could invent a mathematics with A, B, and C that would kind of behave the same way that it would behave with 1, 2, and 3. So I could define, for example, that A plus B equals C, whatever, right? And then you can say, well, that kind of behaves like 1, 2, and 3. And so they're kind of equivalent mathematically if you define how they behave. So there's that definition. What else do I want to say? Okay, some common sets and their equivalents. Okay, so going to define some very common number sets here. There are, and this symbol you guys actually saw me use yesterday, n, which for us will be 0, 1, 2, 3, ... These are called the natural numbers. I will say a warning here. Sometimes n is defined as not including 0. So you have to be careful depending on the source that you're reading. Usually at some point, whenever someone is talking about these numbers, they're going to define at some point what they mean. Is 0 included or not? Not everyone includes 0. So that's just something that you want to be careful about. Although I don't think it's really going to come up in this class. So it's the non-negative counting numbers, we call them, right? So there are 0 things in this set, or there are 1 thing, or 2 things, or 3 things. There are times when it's not even possible to do even that, where you can't actually start counting things like that, which seems strange, but it's actually true. There is also something called set Z. It's Z because of the root word is the German word Zahlen, which means number, which actually also means whole number. These are the, if you threw in the negatives, the negative whole numbers. So it includes plus or minus 1, plus or minus 2, plus or minus 3, ... These are called the integers. Now, clearly, there's an infinite number of things in both of these sets. There's also the set that we call Q for quotient. It's actually named the rational numbers. This is the set. Now, here I'm going to define it by a condition because it's actually very hard to actually write it out completely. But you can think of this as the set of all possible fractions. So it's a set of all things that look like A divided by B, such that A and B are integers, but B is not equal to 0. So here I'm using the condition way of defining the set. This is called the rational numbers. Okay, so it's the set of all fractions. That also has an infinite number of things in it, as you can probably tell. You can just keep counting. You can keep creating new fractions based on what you're counting. Then there are the real numbers. Now this one is very difficult to describe. I mean, you become a math major, you don't even start talking about what these guys really are till like your third year of being a math major. Like okay, you've been through like 2.5 solid years of math. You've done more math than pretty much anyone else is going to ever do in their life. Now let's talk about what the real numbers really are, what all these people use every day and they don't even really know. So it's kind of weird, but it's like a set of all decimal expansions. Set of all points on the number line. Etc. It's called the real numbers. That is not a great definition, but honestly, I cannot define it for you any better than that at this level. Like I have to teach you some advanced mathematics, talk about data kind cuts and all kinds of weird stuff, completion of Q, and yeah, it's also the completion of Q. Never mind. It's intuitively what you think it is. Anything on a number line that you can pick is going to be a real number. Which, by the way, Q, you can plot all the fractions on a number line, and there are a lot of them. And by a lot, I mean a lot. Like any random interval that you would pick, no matter how small, is going to have a fraction somewhere in it on that number line. And between any two fractions you can pick on the number line, there will be another fraction in between them. For example, the average is always between them. And so it's like, you would think like the fractions fill up the number line based on how many there are, but it turns out that it doesn't fill up the number line. There are gaps in what the fractions will fill up on the number line. For example, there's no fraction that can be the square root of 2. And you can prove this, right? So there's like a hole on the number line in the location of the square root of 2, or in the location of pi, or in the location of e. You can't actually fill these in with fractions. So what the real numbers do is they go in and they fill in all the gaps, right? And so we call the real numbers the completion of Q. With Q, the real numbers are the other guys we throw in to fill up and complete the number line. And the guys that are in R that are not fractions, we call these the irrational numbers. And you might think that, well, there can't be a lot of them because, you know, we're just filling in the gaps. It turns out there are actually way more irrational numbers than there are rational numbers. It turns out R is actually larger than Q, and it's like no competition larger. It's actually super larger. Like if I take all the real numbers on the number line and I were to throw away all the fractions, the number of things I would have left over is the same. Like it's like I threw away 0 things. It's that much bigger, right? It's like I took an ocean and I took out one drop out of the ocean and threw it away. It's like you're not going to notice at all. It doesn't make a dent, right? That's the sort of thing that Cantor discovered when I was talking about the tragedies of set theory the other day. And you know, a while ago, people just wouldn't believe it. Like, so you're telling me that both of these sets are infinite, but one is so big, much bigger than the other. Like there are different sizes to infinity. Really? Is that what you're telling me? And one infinity can be so much bigger than another to the point where you can literally throw away this infinity, take it away from this other infinity, and that other infinity won't even notice that anything's missing. Yeah, yes, that's exactly right. There is also the set of complex numbers. This one is a little bit easier to define because it's the set of all, because you can use real numbers. So it's the set of all a plus ib such that a and b are real numbers. These are called the complex numbers. We ignore them, but we need guys like this for when we want to take square roots of negatives, which we don't, but if we did want to do that, we could. So it turns out now the equivalencies of these numbers are the following. The set of natural numbers has an infinite number of things in it, but it actually has the same number of things as a set of integers, right? So me throwing in all the negatives doesn't actually change the numerical equivalence. It's the same number of things. It's the same size. And in fact, when me taking all these positive numbers and negative numbers and creating new fractions with them and creating all these new numbers to throw in, so I take the integers and I throw in a half and 3/4 and 15/17, and I throw in all these new things in it. It turns out I don't actually get more things. That still has the same number of things in it. It turns out, though, that once you realize that, well, Q doesn't fill up everything in the number line, let's fill in everything on the number line, let's fill in all the gaps. We get the real numbers when we do that. When we do that, though, it turns out we, for now, found something larger. This is actually, all of these guys are actually smaller than how many real numbers there are. And they're smaller than how many real numbers there are by a lot, like seriously a lot. Like the real numbers won't notice if the fractions were missing. Like they wouldn't notice, right? You know, like there's, oh, how many of it, is anyone missing? No, I think we have the same number of people here. Okay, cool, let's go. Let's go. They leave on the field trip and they leave all the fractions and the integers behind. And they didn't notice that they're not on the bus, right? It's like that. That's also equivalent to the number of complex numbers, by the way, which is really weird because you can visualize the complex numbers on a two-dimensional plane. And basically what this is saying, the number of points on a line and the number of points on the entire two-dimensional plane is actually the same number of points. Which sounds crazy. Like, I mean, you're talking about, it's one line in an ocean of space. How is it that if I were to plot all the points on the line and I were to plot all the points in two-dimensional space, I have the same number of points? Is that what you're telling me? Yes, that's what I'm telling you, right? Infinite sets get weird, okay? So we also mentioned that. But those will come up, as well as there's times when I'm going to want to say things like this, and I want you to know what I mean when I say things like that. So that's just a definition there. What else do I want to define? Kind of bring it back down to earth now, not talk about infinities anymore. I want to talk about something called the universal set. So it turns out that when it comes to set theory, we are, and this is true in probability and statistics as well, we never actually do anything in a vacuum. So anytime we create a set, we always imagine that there's some bigger set in the background from which we created that set. In other words, we're kind of saying every set in the universe is actually a subset of some larger set, right? So even what we think of as sets, they're really just subsets of some bigger thing in the background. There's this thing that exists from which we can create sets. And so there is like a universe out there in which all our sets are living in and they're playing around in. And this set is called the universal set. And it's not unique. It changes based on context. So we can talk about the universal set of numbers. We can talk about the universal set of integers. We can talk about the universal set of whatever, right? I can just say, this is my universe. These are all things that can possibly exist within the context of this problem. Every time I create a set, it must be created from this list of things. List is a bad word. There are things that you can't list. Like you can't list all the real numbers, for example. There are so many real numbers that you can't even put them in a list. You can't say this is the first and the second and the third. Like you can't even do that. There are too many. So sets are always considered to be subsets of some larger set, potentially larger. In the background called a universal set. And emphasis on the word a. It's not unique like the empty set. This is denoted by a fancy uppercase U. Now let's talk about another definition, the complement of a set. This is the set of all elements in the universe that are not in A. So you have a set, pretty much think, in our universe, who is not currently in this set? What you're describing is called the complement of that set. This is denoted A complement, or some people like A prime, or some people like A bar. Jhevon will use this most of the time, out of habit. But if you're reading some other book where they're talking about sets and you see these other symbols, they probably mean the complement. And they are read the complement of A or more commonly we just say A complement. Right? So if I say A complement, this is what I mean. I'm talking about everyone in the universe that's not in the current set A that I'm looking at. Let's give you a quick example. Let's say for the purposes of a problem, I define that my universe is 1, 2, 3, 4, 5, 6. In other words, I am pretending that no numbers exist other than these 6 numbers right here, right? There's nothing else in the universe, right? For the purposes of this problem, right? So I define my universal set to be that. And suppose I said, okay, my set A here is 2, 5, 6. So before I could just say, oh, A is a set with 2, 5, 6, and everyone's like, okay. But now I'm defining, okay, this set 2, 5, 6 lives in this universe, right? Meaning there are no other numbers other than these 6 numbers. And here's a set that has these 3 numbers, right? Then I can say a complement is actually going to be all the guys that are in the universe, but that are not currently in A. And what would that be? Well, the number 1 would be in A complement. 2 would not be in there because it's an A. The number 3 would be in A complement. 5 is not an A complement. 6 is not an A complement. The number 4 would be an A complement. So A complement would be this set. The set of everything in the universe that's not currently in the set A. That's it. How about Venn diagrams? Venn diagrams named for, it's named after a guy, John Venn. I think it's John. You know, sometimes you use someone's last name so often you don't remember what their first name is, I think. I think it's John. Named after John Venn. So people, for whatever reason, people normally leave this as an uppercase V whenever anyone writes down Venn diagram. There are things that are named after people that they use it so commonly that they started just not capitalizing it. But Venn diagrams, the word Venn is usually still capitalized. Named for John Venn. These are diagrams that allow us to visualize sets. Which can be very useful in solving a problem. So here, they consist of one, a universe represented by a box and sets in that universe. And these are circles or ovals. So it looks like this. You have a box. Normally you write U in the corner. And you can think of a set as being like here, like the set A. So for my U equals 1, 2, 3, 4, 5, 6, I can say, and my A was the 2, 5, 6. I can say, oh, there's 2, 5, and 6 in here, and then there's 1, 3, and 4 out here. And I can actually represent that by this picture. Usually, though, Venn diagrams focus on cardinality. So you don't actually list, so we don't normally list members. But rather, how many members are in each region. So, example. My universe is this, and A is this. Notice this means that the size of the universe is 5. There are only 5 things in this universe. The size of the set A is 3. So my Venn diagram representing this situation I would have a U up here, I would have A in a circle here, and I would actually write the number 3 in here and the number 5 out there. I wouldn't actually list the A, B, and the C. I would just write there are, no, not 3, sorry, not 5. There are only 2 things out here. So now I can say there are 2 things in A complement, but there are 3 things in A, right? So, and in total in this universe, there are 5 things. There's the 3 plus 2 things, right? So 3 elements in A, 2 elements in A complement. So total of 5 things in the universe. And this actually helps us to solve a lot of problems once we start realizing how many people are in these different situations. That can be very, very useful. Okay, let's talk about operations on sets. So now I told you about pretty much everything I actually want you to know about sets definition-wise. So now let's actually start doing some math with them. So I invented these new objects called sets. How do we use them mathematically? How can we manipulate them? How can we, do computations with them, things of that sort? So that's what we're going to talk about now. So let A, B, be sets in some U. Then definition. The union of A and B, denoted A, U, B, is defined by A union B is the set of all things such that X is in A, or X is in B, or X is in both. So if I look at the things that are in either set, one or the other, or potentially both of them, I'm saying I'm looking at things that are in the union. It's like I join these two sets, I put everyone in a group. If there's the same guy in both sets, then of course when I put everyone in a group, we ignore the repetitions. So we don't like list that guy twice, but it's like everyone that's in either set. This is called the union. And it's read, how we say it, A union B. So that's how I would say it in words. Because like I said, it's not just important to know what you're talking about. You have to sound like you know what you're talking about. So you don't say A U B. People are like, what are you talking about? No, you say A union B. Oh, this guy's smart. He knows what he's talking about. He's using big fancy words like union. Okay, so that's what they mean. I will give you some examples shortly. Let's run into the other one. The intersection of A and B, denoted A intersect B, is defined by A intersect B is the set of all things such that X is in A and at the same time, X is in B, right? So it's the set of all elements A and B have in common. All elements A and B have in common. Which I want you to appreciate. This might be nothing. This might be the empty set, okay? So A could be the set of A, B, C. B can be the set of 1, 2, 3. And actually, what is A intersect B? The answer would be the empty set. If I asked, what is A union B? It would be the set including A, B, C, 1, 2, 3, which is a very bad password. But the union will just group them all together, and the intersection just finds who do they have in common. And we can do these kind of operations on sets. Definition, we want to define the set minus. This is a set denoted A minus B, or A slash B, like that. This is more archaic. Very few people use it. Like only the old school classical guys use that now. This backward slash, this guy was classically trained. He's probably from Oxford or something, right? So yeah, more archaic. We don't really use this anymore. We just use the minus sign. It is defined by all the young kids now going around doing this. The set of all X such that X is in A, but not in B at the same time. So that's set minus. At the moment, that's all I want to tell you about in terms of operations. But of course, I will give you some examples later. Visualizing the above. Okay, so let's use our concept of Venn diagrams to start talking about these operations. So how I would look at A union B. I can think of a set A and B. And if I want to visualize what does it mean to take the union, it means I am going to look at everything that is in A or B or both, right? So it's like I'm taking everyone in these two situations. Now, I want you to be aware of a possible, is for A and B to be completely separated. This is A and B are disjoint. But we do not assume this unless we have some reason to know it. But we don't assume this generally. You always want to draw things where you have the most amount of overlap as possible in general, unless you specifically know different. And that's because you don't really know how many people is in every situation. Potentially, there's going to be an overlap that you drew in your Venn diagram where there's no one in it, and that's fine. You just write a 0 on your Venn diagram. It's totally fine. But then if you separate them and there was someone supposed to be in common, now you've just lost that person in how you're setting up the problem. So it's more beneficial to always draw things with the most overlap possible. And then you can say that there's 0 things in these overlaps if it turns out to be that case. Whereas if you draw them separately, you no longer have that option. We will draw Venn diagrams to have as many overlaps as possible in general. The overlaps may be empty. And we would simply label them by 0 in that case. Okay, but that's how I would visualize the union. Now, when I'm talking about the intersection, here's A, here's B. I'm thinking of these guys only the overlap. I don't care about what's in A but not in B or any of that. I care about what's in both at the same time. That's how you'd visualize the overlap. What about the set minus? A minus B. This is visualized as these guys over here, right? It's a set of all things that are in A, but you throw away all the things that are also in B. And so that's the set minus. Of course, you can go the other way. It can be B minus A. Now remember, it's not arithmetic, right? So it's not like you can get a negative set, like you could get a negative number or something like that. That doesn't exist. Like if you can get the empty set is the lowest you can go. But really the set minus is itself another set, right? So you're just talking about the set of all things that are in the set, but not in that set at the same time. What if everything in this set is also in that set? Then the set minus is the empty set. But you're never going to go beyond that. This would be that. So you're looking for all the guys over there. It would probably be nice to talk about A versus a complement. So when I say A, I'm thinking about everything here. Everything in the universe that's in that group. If I say a complement, I'm talking about everyone out here. That's a complement. I'm thinking, no, I won't do it. We're going to go over time too much. Can't just abuse it all the time. Okay, so what I'll do now, because I was going to start the examples. I was going to do one example and then leave the rest for you guys to try, and then we finish them on Friday. But I just decided I'm just going to write down all the examples and have you guys try all of them, and then we do all of them on Friday. Yeah, so let's do that. Let's do some examples, because we've been talking about concepts for a while, and I don't know how much of it is going over your heads or not. So let's just talk about examples. One, use Venn diagrams. Now, it's very important. Diagrams are important for visualizing and illustrating things, but they do not count as proofs. It's a very strict rule in mathematics that pictures cannot count as proofs. Because human perception is very limited. Just because someone can draw a nice picture and tell you a nice argument about it is often very irrelevant. Which I know is strange, because in life and the business world, it's all about the presentation, right? In math, we know better. We're like, it doesn't matter how nice your presentation is. Like, if your argument is flawed, it's flawed. So while you can't prove anything, sometimes you try to convince yourself by kind of seeing something visually. Use Venn diagrams to, I will say, conjecture. We can make a guess the connection between A. So I want you to look at this set. A intersects B, and I want you to find its complement, versus I want you to find A complement and then union that with B complement. Draw a Venn diagram for each one. Tell me what you think. How do they relate to each other? Another one is A union B and its complement. So draw that, figure out what A union B looks like on a Venn diagram, shade everything else, and then look at this one. And tell me what is the relation between these sets? Is one bigger than the other? Does one have more things than the other? Who has more things than the other? Which one is going to always be bigger? Which one is always going to be smaller? That sort of thing. Two. Suppose I say my universe is the set of natural numbers. My set A is the set 1, 2, 3. My set B is the set 3 and 4. My set C is the set 4 and 5. My set O is the set of all positive odd numbers. And my set E is the set of all positive even numbers. All right, so hopefully you know what that is. 1, 3, 5, 7, 2, 4, 6, 8. I want you to find the following. Find A intersect B, A intersect C, A intersect E, A intersect O, E intersect O, A minus B, C minus A, N minus E, E minus N. And 3. This is the last one. Now my universe is 1, 2, 3. First positive 10 integers. A is the set 1, 3, 5, 7, 9. B is the set 2, 4, 6, 8, 10. I want you to find A intersect B, find A union B, find A minus B, find A complement, find A intersect B complement, find A union B complement. Yes, we'll stop there. So of course, I'll leave these in the notes on the class video, but those are the guys we'll do next time. And then we shall move on. Talk about a very important concept next time called the inclusion-exclusion principle, maybe some other things, and then moving on to probability afterwards. And then I'll also want to give you some actual examples on Venn diagrams, like word problems that you can use Venn diagrams to figure out. Yeah, so that's what's coming up, and we'll start probability next week. That is it. Thank you for your time and attention. Try these for next time, and I'll let you guys go at this point. So yeah, I will see you guys in the next one.